Hey there and welcome to another LeetCode video. So today we're going to be doing problem number 516, longest palindromic subsequence. And we are saying find the longest palindromic subsequence in the word we have. And the difference between this and a substring, so let me show you real quick here. Let's just do this. So if we have, let's see, okay, there we go. Okay, so if we have this, the longest palindromic substring has to be continuous. So it would have to be this. And so let's think of how we would do that first. So let's say this problem was the longest palindromic substring instead of subsequence. Let's think of how we would do this. Well, I think this is actually another problem, so you can look that up, but I'm just going to explain how to quickly do something like that, and then we can figure out what changes we'd have to make to do this. So what we can do for that, if it has to be a continuous sequence of letters, is we can actually start at every single location, at every single letter, and at every single spot between the letters. So let's say we start at this, location B. We can simply expand a left and right and check if we're out of bounds or not, and if the two characters are equal. And that means that we still have a palindrome, and we can keep expanding and keep expanding and keep expanding until we don't. So in this case, we're out of bounds, so we wouldn't have a palindrome, right? So then we can start here now, and we would expand out. Okay, so that works. Then we expand out again, and we can't. So the longest is this. So that's our longest so far. Then same thing, we start at this B, and then this wouldn't work, so we would stop. We'd start at this A, this would work, then we're out of bounds, so this is the longest. And now the other thing, that would give us all our odd ones, right? Like if we start at a letter and we expand out, it's going to be like 1 plus 1 plus, or sorry, 1 plus 2 plus 2 plus 2, so it'll give you only odds. And for evens, what you need to do is you actually need to start at a left and a right letter, and so it would be like this. You'd start at every two adjacent letters. So you'd start here, you'd be like, okay, that works. Expand out, can't. Okay. Then you'd start at these two letters, expand out, can't. These two letters, these are already not equal, so that doesn't work. And then these two letters, and they're already not equal. And that's how you would get every single unique, or that's how you would get the longest palindromic substring. Now for a subsequence, we are allowed to actually get rid of letters at any point, as long as our order is maintained. So this is a palindrome because we can just chop out this letter. And so what we would do with this is, typically when you can chop out letters, a good idea, there's quite a bit of problems on LeetCode where you can do these subsequences, and for most of them the answer is going to be dynamic programming. And so what we would actually have to do is we would follow the same thing as the unique palindromic substring, but instead we are going to start at every odd or even. So let's say we have a left and a right, which is the index of the left and the right letter, right? And so for the odds, our left and right are going to be the same. So let's say it's going to be left equals 0, right equals 0. They're going to be the same. And then all we do for I'm going to talk about the recursive solution, but this LeetCode problem is kind of annoying because the recursive solution, the dynamic programming recursive solution, actually doesn't pass. So then I'll talk about the trick you need to have it pass, or the other way you can have it pass. So the recursive solution, let's say we start with these, right? And we can just have a for loop for every single letter and for every single combination of letters. And so let's start at these, and we'll say, okay, if they're equal, then all we have to do is do 1 plus, and then we branch out, right? So then when we branch out, now our L becomes -1, and then we're out of bounds. So that's going to be kind of like a base case. Whenever we're out of bounds, we're just going to return 0. So we're going to branch out, then the substring starting here is going to be 1 because our recursive case will be 0. Now let's say we start here. So same thing, we're going to do 1 plus. We're going to go over here and go over here. Now this is 0, and this is 2 because this is index 1. So then we could say, okay, are they, if your two letters are equal, it's pretty straightforward. You just do 1 plus, and then you do the next recursive case. So in this case they're equal, you do the next recursive case, and we're out of bounds again. So we can't do anything there. We can't skip something if we're out of bounds. So that's going to be that one. Now let's say we start here. So let's try to do this again. So we go here and here. Okay, they're not equal. So we would have a 1 originally, right, because this would be equal to itself. But when we branch out, these are not equal. And so what we'd have to do is we'd have to actually try to skipping either one and seeing what's our max value going to be. right? And so let's say we skip this A. So instead of branching out twice, pretty much, or sorry, if they're not equal, what we need to do is we need to try to go over here, and that's going to be one case where B is this, or this is the right, this is the left, and then the other case is we keep this A, but then we branch out over here. So this is the right and this is the left. And so you can see kind of anytime they're not equal, we would just do the max of going left or right. So we'd keep one index the same, but then we would go out with the other one. And if they are equal, then we just do 1 plus. We go left and right. And there are other problems like this, like longest common substring, I think, or longest common sequence. And that's kind of the problem we're going to code up. And so the problem we're going to code up is going to be similar to the recursive solution for this, except the recursive solution for this doesn't, like I said, doesn't pass on LeetCode. So we're going to code up something else, and we're going to do a little trick. And so actually, if you can tell, by the way, so remember, you can either start at one letter, that being the same, so left and right are both one letter, or the other case, when we do this loop, we can start, what would be our actual optimal solution here? So our optimal solution would look something like this. Our left would be 1, and then our right would be 2, right? So we're going to try every single possible, we're going to try left and right equals 0, 1, 2, 3, 4, 5, and then we're going to also try left equals 0, right equals 1, and then left equals 1, right equals 2, and so on to get every single odd and even. So this would be the case for an even, and so left is here, right is here. So let's just look through this real quick, how the recursive dynamic programming solution would look. So here we would have a B and a B, so we would do 1 plus, remember, and then we would branch out. So then our left becomes 0, and our right becomes 3. Then we would say, okay, so actually this wouldn't be 1 plus, by the way. So if what we would actually have to do is, if the left and the right are different and they're equal, it would actually be 2 plus, right? Because it's 2 letters. But if the left and the right are the same and they're equal, then it would be 1 plus. So that's a simple thing you can do in the memoization, where if you're left and right and they're the same letter, then you do 1 plus, and if they're 2 different letters, then you do 2 plus. But anyway, so this is 0, this is 3. Now they're not equal. So remember, we can branch in either direction. So let's try to branch left. Okay, so we try to branch left, we're out of bounds. So that's going to be one of our base cases where if we're out of bounds, we are just going to return 0. So it's going to be some max, right, of the left and the right. So the left is going to give us 0. So that doesn't work. Well, now let's try to branch, instead of to this A, let's try to branch to this B. Okay, well, so now we're going to be at this index and this index. And those are equal, and they're 2 different ones. So then it's going to be max of 0 and 2. So it's going to be 2 plus 2. And then the other thing you can do is you can actually cache all these different indices. And so the number of different indices you can have here is, let's say the length of this string is s. All of these index can be up to length s, so it would be s squared. So the complexity of the memoization solution would actually be s squared. And the complexity of the next solution I'm going to show you is also s squared, but the problem is just the way they have the whatever they're testing on LeetCode, the memoization doesn't pass. But actually, if you do want to code this memoization and you want to code up the true dynamic programming solution, that does pass on LeetCode. But let me show you the other way, and this is actually going to be easier to code, and it's like another problem. So instead of doing that, let's do this, right? So let's take this BBAB again. And what do we know for a palindrome? Well, a palindrome is equal to its reverse, right? So what we can actually do is we can reverse this string. So the reverse would be B, A, B, 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 right? Okay, and what we can do is we can actually do a longest common subsequence on this, not just a palindromic, but a longest common subsequence. And let me just go over longest common subsequence really quickly. So actually, let me just redraw this a little bit so make it better. So B, 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 A, B, and then the reverse is B, A, B, B, B. Okay, so now it's pretty straightforward what to do in a longest common subsequence. So all we do is we start at this index. So we're going to have the same thing. We're going to have two different values. So let's just call this top and let's call this bottom, let's say. Okay, and they're both going to start at 0. And then our cases are, first of all, our base case, if one of these is out of bounds, then obviously, like let's say our top index is here, then obviously the longest common subsequence can't be any bigger, so that's going to return 0. So if any one of these is out of bounds, that's our base case, and then we're going to return 0. Now we're going to compare the two, and if they are the same exact letter, then we're going to include that in our subsequence. And so that's pretty straightforward, right? So like these two should be the same exact letter, so we're going to include them. So then we're going to do same thing. We're going to do 1 plus, right? Then we're going to be over here as our next two letters. Now, if they're not the same, we're going to make a choice. We're either going to move here or move here. And so let's see what that would look like, right? So let's say, and then we're going to get the maximum. So they're not equal. So let's say we move this top one. Well, if we move this top one, it's still not equal to A. And then now we can move this, right? And then clearly you can see that this is not going to be our best solution, because the most times these can be equal is twice now, so that's going to be a problem. So that's not going to be what we're going to want to do. So the optimal solution is actually going to be, instead of moving this top one, is we're going to move this bottom one. And so we're going to move this bottom one, and yeah, once again, so if they're not equal, we just say max of, let's say, top plus 1, the dp of that, or bottom plus 1, right? We move one or the other, and we just return the max. But let's say we move this bottom one. Now these two are equal. Okay, perfect. So now we're going to have 1 plus 1. Then we're going to move them both. So now they're going to be over here. They're going to be equal again, 1 plus 1 again. Now we are here and here. And so once again, we can move either one. So if we move this, then we are out of bounds. So that would be the worst solution, but instead we'd want to move this. And then this would be equal to this, so we do 1 plus 1 plus 1 plus 1. So I'm going to code this up, and then it'll be a little bit more straightforward on how it works. But basically, yeah, all you need to do is you need to do a reverse of the string, and then you just need to do a longest common substring. And the longest common substring of a string in its reverse is going to be guaranteed to be the most common, the longest palindromic subsequence. And you can try a few different equations. You can try a few different substrings to and see that, and then you can you can show it to yourself that's the case. And even if you do have something in its reverse, right? Like let's say we have this, and then we have CBA, or let's just say we have some letters in here, right? So Z, X, whatever, CBA. So you might think that like, oh well, if I reverse this string, now these will match, and there's going to be an issue. Well, really, what's going to happen is it's going to be like this, right? So then there's going to be some stuff here, whatever, and then ABC, right? Or it's actually going to be, no, it's going to be CBA as well here, I believe. And so the longest, let me see if that's right actually. ABC, ABC. So this would actually be ABC as well, I believe. Yeah. And so the longest common subsequence, even though these do match, is actually going to be this and this. And so even though there is a reverse, if you take this stuff out in the middle, then this whole thing is also a palindrome. So basically no matter what you do, even if you do have some string in its reverse in the actual original string, it'll be fine. And so let's actually code this up, and then I'll show you. It'll make a lot more sense once we're coding it up. So we're going to code up, remember, we're going to code up the longest common subsequence. And you can actually find that problem on LeetCode as well, but this is going to be the code for that. So what we need to do first of all is we need to have this reverse string. So let's just say rev s equals s, and then that's just going to be this reverse. I believe you can do that, so let's just try to print that just to make sure. Let's just return 1 or something for now. Okay, so B, 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 A, B, and then, yeah, so this is the reverse. Okay, perfect. So that's what we wanted. Now we do need to have a memoization array, because this is going to be a memoization solution. And yeah, this is going to be the same time complexity as this original one where we did have the left and the right, but this one passes on LeetCode. So technically it should be the same time complexity, just the way they have the questions, one pass and one doesn't, so it's pretty close. Okay, so now what we need to do is have the visited, same as usual for memoization. Now we just need to code up the DP, right? So def DP. Remember, we're going to have two indices. We're going to have the top index and the right and the bottom, so let's just call it top and bottom maybe. Okay, and remember that our base case is when we're out of bounds on either of them. So if top is greater than or equal to len s. So technically, actually, Yeah, so these should be the same length, so we can just, oh, well, but that doesn't really matter. So this is just return 0. And then, so if top is greater than or equal to, or bottom is greater than or equal to, remember s is going to be the same length as res s, so we can just do this, or rev s. Okay, so we can return 0. Now our other case is if our index has already been checked. And that's also important because you can get to the same index multiple times and you're going to have a lot of repeated work, because if you have differing indices, that can happen, right? So if you have like, I don't know, let's just say like A, B, C, D, and then you have E, F, G, H. So they'll start here, but on the next, you remember you get to move one of them. So let's say you move this one, then you move this one, you're going to be here. But you can also move it the other way, right? So you can move this one, then you move this one. So you're going to be at the same place. And it doesn't really matter how you got to these two indices as long as they're the same. Like the previous work doesn't matter for the DP. Okay, so let's just make sure we do that. So if top, bottom, and visited, then we're going to return that. Set top, bottom. Okay, now remember, if the letters at the current index are the same for longest common substring, we are going to add 1 because we're always going to take that, because we can always, since we're popping other letters, the optimal solution is just always going to be greedy, where if the two letters are the same, we're always going to take that. So we're just going to say res equals 0, and then we're going to say, or actually we're going to say res equals 0, and then we're going to have multiple cases here. So if s top equals, and then this is rev s bottom, then we are always going to just do res equals 1 plus the biggest one, right? So we're going to try to, or sorry, it's not going to be the biggest one. So here, when they're equal, we're going to just do 1 plus, and we're going to move them both, right? So if these two are equal, we're going to move them both. We're not going to move one or the other. We're only going to move one or the other if they're not equal. So then we just do dp of top plus 1, bottom plus 1. Okay, else, now we try to move each one. So res equals max of dp top plus 1, bottom. Now we try to move the other one. So dp top, bottom plus 1. Then we just cache that, right? So visited top, bottom plus res, return res. Now we just call our dp and we return that, right? So return dp, and we're going to start at index 0 for both. Okay, let's try that. Okay. Okay, so that did work, but yeah, you can code up the other dynamic programming solution. But honestly, once you realize that this is the reverse, once you know this trick, I think coding up the longest common substring is also just more intuitive than this palindrome where you are starting at. The difference between this palindrome is you would have to have a for loop as well, right? So you'd have to have like for I in range len s. You'd have to pass in I and I, and then you'd also have to pass in I and I plus 1. You have to pass in all these combinations because I and I would give you the odd, and then this would give you the even. So you'd have to do that. So if you did code up the other one, that's what you'd have to do. Okay, so let's think about the time and space complexity for this one. All right, so time. So how many states can we possibly have? So we can have this top and this bottom, and top can be length s and bottom can be length s, and we have it memoized, so we're never going to be doing the same work multiple times, right? Once we compute any one of these, we're going to be done. So the most possible cases we have is n squared here, which would be n is the length of s. And space. So this same thing can also be completely full. So if this visit is completely full, every state we have is n squared. Okay, so it's going to be an n squared solution, and hopefully that makes sense to you. And if you have any questions, leave them in the comments. And if you want to try the memoization with the left and the right pointers and see that fails, and then you can also try to code up the actual true dynamic programming solution for that one, and that would actually pass in LeetCode. So that would be a good challenge to do if you're rusty with bottom-up memoization. or bottom-up dynamic programming. And if you want me to do an actual how to do that, I can do that in another video. So can you please like and subscribe this video if you like this content, and I'll see you in the next one. Thank you.